Now we have to add an absorber. Okay, so for that matter, we have to bring in an absorber, which is a radfrac column. So we will choose this icon. Okay, so this icon, we can increase it a bit. The gas enters from the bottom. So this is the gas entering, and there will be a vapor distillate. So this is the vapor outlet, and this will be the rich outlet, rich amine outlet, and this will be the lean amine inlet. So we will name them as lean am. This will write at leach am. So this is lean amine, and this is rich amine, rich with CO2. So here the amine is being fed without CO2. CO2 is coming from here through absorber feed. This gas is having CO2. So amine is absorbing CO2, and this stream is rich with CO2. And this one we call gas out, and this gas out will take out most of the gaseous part which is not absorbed by amine. For instance, we have nitrogen, we have oxygen, we have argon. So amine doesn't absorb them. So nitrogen gets released from the top, oxygen gets released from the top, argon gets released from the top, and some amount of carbon dioxide also gets released, because not all the amount of CO2 gets absorbed in the lean amine. Okay, so some amount of CO2 will always get lost through the gas out, although we want to minimize it because we want to maximize the capture of CO2. That we will take care in the subsequent sections. And another thing that we have to ensure that we have another feed, that is the recycle feed. At this moment, we do not have a stripper, so we do not have the recycle at this moment, but we have to keep some provision over here. So we keep the provision for a recycle, which is over here. So this is the provision of recycle. It comes from somewhere. Let us take it as watt wash. We'll call them watt wash. The significance of the name is something like this. Here you can see in the stripper we have a condenser. And you might remember the stripper is having partial vapor liquid condenser. Partial vapor means all the CO2 portion is going out, and here it will be liquid distillate which is water rich. It will always have lot of water into it. So that water we are not going to lose. We are recycling it back to the absorber. So this portion is being washed with the water. So think about the recycling later. At this moment, let us assume that a water wash stream is coming from somewhere. We will replace it with the recycle later. So lean amine, we have to provide the input. As it is said, the amine stream typically 40 kg per second and 40 degrees centigrade. So it is 40 degrees centigrade, 1 atmosphere pressure, and the mass flow rate is 40 kg per second. And typically the amine is having the composition of 45% MDA and 5% PZ. So we will have the mass fraction of 0.45 This will be 0.05 and rest will be water. So water will be 0.5. Total it is 1. Right? So this is the amine inlet and water wash outlet. Right now we do not have any recycle stream. We will assume something. What we'll assume? That it is coming out at 40 degrees centigrade. In fact, we have the information. Yes, the partial vapor liquid condenser maintained at 40 degrees centigrade. So whatever the H2O rich distillate that is coming out of the condenser of the stripper, that will have the temperature of 40 degrees centigrade. So we will assume that this is 40 degrees centigrade. And for the time being, we will keep a very small flow rate of 2 kg per second. It's a kind of dummy stream for now. So now we have to go to the block. Okay, we have to name them. This block, let us name as let us name it as watt flash. This is watt flash. And we will name it absorber. This is an absorber. Okay. Now let us go to the absorber. Okay. Now always remember, do not try to get a rate-based calculation in the very first step. First, let us run it in the equilibrium mode. First, let us converge in the equilibrium mode. Then we will take a rate-based calculation. Okay. So let us take it as equilibrium. What are the number of stages? It says the absorber has 10 theoretical stages. So we will have 10 theoretical stage over here. Absorber, that means there is no condenser and no reboiler. Simple absorber. The streams, the ABS feed, it is at the bottom. So we will take the 10th stage, on 10th stage, and lean amine and watt wash we will put from the top of the column. So both of them first stage, above first stage, above first stage. Okay. So from the stage 1, the gas out stream is coming out as a vapor, and 10th stage, the rich amine is coming out as liquid. The pressure, let us keep it as 1 atmosphere. Okay. So that's how the absorber is fixed in the equilibrium mode. We will talk about the rate-based calculation later. So first let us run it. Okay. It comes to stability very quickly. Now let us watch the flow rate of CO2 that is coming through these streams. Okay. So for that, we have already defined over here. So look at the property set. It is PS1 mass flow rate. We have already defined. So we will go to the stream results. There we will take a label and we'll call it CO2 and property set PS1. Okay. And we do not need to see the temperatures, but we can see the temperature later if you want, with 1 digit after decimal point. Pressure we do not need to see because it is all atmospheric pressure. And mass flow rate, definitely we want to watch mass flow rate. Okay. Yeah, that's what it is. So, okay. Yes, so the mass flow rate has been given in kg per hour. So let us again go to the setup and unit sets. Let us define a new unit set US1, and this US1, we take the mass flow rate as kg per second. Yes, we'll take temperature as in centigrade and mass flow rate in kg per second. Okay, and then we will choose unit set as US1. Okay, we'll go to the stream result, and PS1 we will change the color. Okay, yes, so this color, or we'll change the color red. Yeah, this one. So this is the amount of CO2 in kg per second. Okay, so this is the total mass flow rate, 15 kg per second, and CO2 mass flow rate is 1.03 kg per second. So this is the raw feed, and at this moment we do not need temperature and mass flow rate. Okay, mass flow rate will read, not temperature. So that will make it cleaner. Yeah, so the total mass flow rate is 15 kg, out of which 1.03 kg is CO2. Remember, 0.65 kg is going out through the gas out. Nothing is getting absorbed. Why it is behaving so? Because we have not used any reaction. We have said it is an equilibrium mass transfer, but we have not posed any reaction equation over it. So we have to painstakingly add the reactions that has been set over here. Okay. So for that, let us go to the reactions, set new. So choose this React dist. First, let us set the stoichiometry. So it is H2O to H2O, and this one is H3O plus and OH minus. Both of them are 1. Okay. This is equilibrium reaction. Next one is also equilibrium reaction. So it is HCO3 minus and H2O. Both of them will have coefficients 1. And then this is CO3 minus minus and H3O plus. Okay. Again, new equilibrium. PZH plus H2O 1 and 1. Then it is PZ and H3O plus. Okay. The fourth one, it is HPZCOO plus H2O, then component PZCOO minus this one and H3O plus. And the last equilibrium reaction, which is MdEA plus H2O and it is MdEA and H3O plus. Okay, so these are equilibrium reactions. Now in these equilibrium reactions, the reacting phase is liquid, concentration basis is mole gamma. First two equations are calculated from Gibbs energy, and the other three, their equilibrium constants have been given. So let us go to the equilibrium. The first one is taken from Gibbs energy, reacting phase liquid and mole gamma. Second one is also like that from Gibbs energy. For third one, we will use this particular equation. So it is A Okay, there is a mistake over here. Actually, it will be ln of k equilibrium 3 is this. This will be ln of k equilibrium 4 is this. This will be ln of k equilibrium 5 is this. Okay, small error over here. Anyway, so we'll keep writing. A is 18.135. B is 3814.4 by T, and there is no C over here because ln T term is not there. dt is there. D is this one. So this is minus 0.015096. That is for the third equation. The fourth equation will be 14.042. This one is 3443.1, and there will be nothing else. The fifth reaction, it will be minus 56.2. This one is minus 4044.8. There we have ln with a coefficient of 7.848, and there is no D. Okay, so all the equilibrium equations have been set. Now we go to the kinetic reactions. So add them first. So this one is kinetic. We'll choose here as kinetic. What are the components? CO2 and OH. So this is CO2 and OH. Both of them are 1 with exponent 1. HCO3 minus. Okay. So this is the reaction number 6. Reaction number 7 will be again kinetic. This will be exactly opposite. HCO3 converts into CO2 and OH minus. Then 8th reaction, kinetic, PzCO2H2O. PzCO2H2O with all coefficients, and H2O will not go into the exponent over here. PzCO minus and H3O plus here we have to put 0 because H2O is exactly not going into the equation in the exponent. Okay, so that we have to remember. Then ninth equation is PzCOO minus plus H3O plus will be equal to PzCO2 and H2O. Okay. Then 10th equation is kinetic reaction with PzCO double minus, the last one, H3O plus then this one plus CO2 plus H2O number 11. This is kinetic. This one plus CO2 plus H2O remember for H2O the exponent will be 0 and this is PzCO minus H3O plus. Then 12th reaction, kinetic. It is about MdEA plus CO2 plus H2O. Again, 1, 1, 1, 1, 1, MdEA plus HCO3 minus one, and the last kinetic equation we have to set MdA plus HCO3 minus This is MDA. This is CO2, H2O. Okay. So 8 kinetic reactions, and the reactant phase is liquid and concentration basis molarity. So we have to just add in the power law kinetic expressions which are given over here. So kinetic factor K is equal to 4.32 10 to the power 13. And this one is 13249 calorie per mole. Okay. Then go to the second one. K is 2.38 10 to the power 17. And activation energy 29451 calorie per mole. Eighth reaction 4.14 E10 8038.3 calorie per mole. Ninth reaction 7.94 E21 15758 calorie per mole. Tenth reaction 5.56 E25 18372 calorie per mole. The 11th reaction 3.62 E10 8038.3 calorie per mole. 12th reaction 2.22 E7 9029 calorie per mole. And finally the 13th reaction 1.06 E16 25424 calorie per mole. Okay, so all of them we have set. We have not missed anything, I believe. Yeah. So all of them we have set over here. Now I'm not sure why the stoichiometric is still giving a problem. This one is okay. We have forgotten to put 0 over here, right? And that is the problem it is giving. Okay, now it is okay. Okay, so we have painstakingly added the information on the reaction. Now we can use the reaction and see the changes. Okay, so right now nothing is being absorbed in amine. So what we will do, we will add up the reactions over here. So there are 10 stages, so it is from stage 1 to stage 10. We'll have the reaction ID R1. And we have to provide the hold up because we are using the equilibrium mode. In the rate-based calculation, the hold up and residence time, you do not have to specify. The system itself will take, but in equilibrium calculation, you have to assume some hold up. So here, let us assume a hold up of, say, very low hold up, you put 0.001 kilomole. Okay, it doesn't need to be very high because you do not know actually what will be the hold up. So it's just a wild case, nothing else. And now we can run the string. Okay, so there will be some problem over here. Let us see what is the problem. Let us put 0.01 then. Yeah, now it is okay. Okay, with 0.001 it was having some issues, but with 0.01 hold up it converges. Anyway, we do not have to bother about it right now. Now here you can understand what is happening. Entire amount of CO2 is being absorbed over here in this. Okay, you can see nothing is coming out from gas house. In the previous simulation, 0.65 used to come out from there, but now nothing is coming out. That means entire amount of CO2 has been absorbed in the observer. Okay, so that's exactly what is happening. Now we'll convert it to the rate-based calculation. Okay,